Okay, and we're back. So now we'll continue our discussion about these different t-tests by diving into the actual t-tests themselves. So let's start with the two independent samples t-test. So again, looking at our handy chart, this is a comparison between two groups, and we're observing them between subjects. And so this here is a two independent sample t-test. And so broadly speaking, these are used to test hypotheses about the differences between two population means, as the previous slide, I guess, just explained. In this case, variance in one or both populations is known. And so basically, we're just making comparisons between two independent groups. As you can see, the equations are starting to get a little bit noisier. But really, this is essentially the same as what you've seen. It's just now instead of one sample mean and one population mean, we have two sample means and two population means. Right? And therefore, our denominator is also accounting for the fact that we have those two, right? So instead of just estimated standard error, or something like that, now we're looking at it with consideration of the two different sample means. And on that note too, in this video, I think I'm going to start to speed up a little bit in how I present some of this stuff, because I'll assume that you understand the basics of the math, the equations. Um, if you don't at all, obviously ask questions, because we're here to help. But at this point, I don't want to just beat on a dead horse or something like that when you already know this. I want to make this a more rapid experience for you if possible. Okay, so assumptions of this test, there they are. um, yeah, yeah, I should probably spend more time on this, but I'd rather get to the meat and potatoes of it. So this first example here, we have two independent samples t-tests. And so to provide some context, so say we're asking this research question about if eating slower reduces food intake. Maybe that's something you've heard before. If not, there's this idea out there that if you eat more slowly, more mindfully, you'll actually reduce your consumption. So if people are overeating or want to lose weight or something, or maybe for health reasons, right? They're just trying this out. And so let's say we test this and we take people to a buffet and we give them all access to the same buffet foods. And one group is told to eat fast, and the other group is told to eat slowly, right? Very basic test of this. They can eat all they want, and this is the only difference is if they're told to eat fast or slow. And so we record the total calories consumed. I will say I got this example from the textbook. These are some rookie numbers, right? I've definitely had a lot of meals with more calories than this. And I shit you not, when I was in undergrad, I saw my roommate eat over 3,000 calories worth of chicken nuggets. That was an impressive day. Um, yeah, so these are rookie numbers, but healthy numbers. So we record these. I'm getting sidetracked. Um, and we want to test whether the rate of eating influenced consumption at alpha of 0.05. All right, so you can see here we have the mean and standard deviation as well. And each row corresponds to a different participant. So we have 1, 2, 3, 4, 5, 6 in this group, and then another 6 in this group. So we've got our steps here. Let's start with step 1. In this case, the null is, now you can see it's a little bit different. Now we're referring to mean differences. And so we're saying that, ultimately we're saying that there's no difference in the population means. In other words, the rate of eating has no effect on the number of calories consumed in a meal. Right? These two populations are essentially identical. That's our null hypothesis. And then our alternative is just the opposite, right? It's saying that there is some effect here, and there is some difference between these two population means. In other words, these two populations are not identical. Easy enough. Now let's set our criteria. We already said alpha is 0.05. Here it's a two-tailed test, and since this is a t-test, we'll just account for that when we look up our columns in the table. For our degrees of freedom, since we have two samples now, it's a little bit less straightforward, but ultimately it's still pretty straightforward, I think. We can find this a few different ways. One way is if we know our total N, so our entire sample size, so in this case there were 6 in each group, so that'd be 12. We could do 12 minus 2. We could get the degrees of freedom for one group and the degrees of freedom for the second group and add them together. And that's ultimately what method 1 and method 2 are both showing, right? Is first sample size minus 1 plus the second sample size minus 1. In either case, we'll end up with 5 plus 5 equals 10. In this one, we got 12 minus 2 is 10, right? No matter what we do, we'll end up with 10. And then we'll use that. We'll look up our critical values, and we'll find a critical value of t of plus or minus 2.228. All right, so that's easy enough. So you can see here, or hopefully you're seeing here that there's a pattern, right? That this really isn't that different than what we've done so far. There's just some different math involved at different stages, and we're ultimately just using different numbers or different statistics in the parts of our formula. And so for here, you can see this bottom, what used to be standard error, estimated standard error. Now it's something called estimated standard error for the difference. And to calculate that, we'll use this fun formula here. And yeah, so here we have sample sizes, right? So that's straightforward. But now the numerator looks a little bit different. I won't even S sub p squared, I think is how you would say that. Ultimately, that's the pooled sample variance, right? Rather than just variance like we've used previously. And so to calculate that, if we have equal or unequal sample sizes, we'll have to do this in different ways. In this case, we had equal sample sizes, so it's pretty straightforward, right? And so essentially, we'll just add up these two variances, one for each sample, divided by 2, and then we'll get our pooled sample variance, right? And again, I'm moving more quickly here, but if you need a refresher, all the information about calculating variance, things like that, have been covered previously. It's just now I'm going to assume that you have that knowledge, or at least know where to access that information if you need it. Yeah, so this is just exactly what you saw on the previous slide. Then we're going to use that to calculate estimated standard error for the difference. We're just plugging in numbers here. Right, we have our pooled sample variance, we have our sample sizes, we get an estimated standard error for the difference of 82.66. And then we'll plug that into our formula along with our sample means. The population means, though, that might be a little bit confusing, what we're supposed to plug in here. And fortunately, it's easy, though, right? Here we're just using our population, or I'm sorry. Here we're using our sample means, right? Our observed means to calculate our observed mean difference. And here we're just going to plug in our mean difference stated by the null, right? We're testing our null hypothesis. So we can just plug in this case, 0, because that was the mean difference stated in that null hypothesis, right? So that's easy. And so then we'll just plug all that in. We'll get a very straightforward little math problem, and we'll get a t of minus 0.605. And so now let's make a decision, and we compare our obtained to critical. Here is our t crit. Our t obtained is minus 0.605. And we'll see that it is less than our critical value and does not fall in the rejection region, right? This is a really small t. And so knowing that, we will retain the null hypothesis, right? I think that might be the first time we've retained one in this class. So yeah, doesn't always work out, right? In this case, we retain the null because we had a non-significant obtained t-value, clearly falling in the retain region, I guess, not falling in the rejection region. Okay, and if we wanted to calculate effect size here, something that we've also covered before, so I won't spend too much time on this, right? Telling us how big or large an effect is, more the magnitude, which tells us more meaningful information than just looking at the significance alone. Now, I think we've talked about all these measures before. Cohen's d, eta squared, omega squared. Cohen's d, here's a formula for doing that for this type of t-test. And so you'll see here our denominator is the square root of the pooled sample variance, right? We already calculated pooled sample variance before. Now we're just taking the square root there. Then the top is simply the mean difference. Here's eta squared and omega squared. Let's see. Yeah, so basically these formulas are going to be the same for all of your t-tests. So if anything else, maybe that's one reason to use them is because they're easier to remember. Or you don't have to remember nuances and differences. So yeah, wanted to throw those out there for you. We'll calculate one of those later when we finish our next example, which is right here, a related samples t-test, right? And so now we're looking at the within subjects iteration or version of what we're talking about today. All right, so two groups observed within subjects, related samples t-test. Yeah, and as intuitively stated, testing hypotheses about two related samples. Variance in one or both is unknown. So here's our formula. This one's a little less frightening, I think, than the previous one. To give you some notation here, M sub D is the sample mean difference. Mu sub D is the population mean difference. And S sub MD is the estimated standard error for different scores. Right, and so here this is kind of similar to what we just did, but it is fundamentally different, right? And that previously we were looking at differences between the two samples, and here we're looking at differences within the samples at the participant level, and then we're calculating sample statistics from those differences, right? Or in other words, before we were calculating differences of the sample statistics, now we're calculating sample statistics of the differences within the sample. Hopefully that makes sense. If not, then just stay with me. I promise we'll get there. So the degrees of freedom here, n sub d minus 1. Basically, yeah, same thing as always. Two assumptions, we'll make them. So comparing the mean difference between pairs of scores in the population to those observed in the sample. That's wordy. Basically, let's get down to brass tacks. So we're talking about different scores, right? Ultimately, a different score is what it sounds like. It's a difference. What is the difference? It's subtraction, right? Or it's the value obtained by a subtraction. And so a different score is the score that we obtain by subtracting two scores. So say, for example, we have 4 participants and we gave them test 1 and test 2 and we want to compare how they performed across tests, right? Let's say that, oh, I don't know, this is like maybe a pre-post test, or maybe they had to retake a class, right? And want to see how they compared. So participant A on test 1 scored a 93, and then on test 2 scored a 98, right? And so we can see that's a different score of minus 5, right? 93 minus 98 is minus 5. Participant B got an 87 and an 84. So what's the difference score? It's plus 3, or just 3, right? And so then we can do that for the other two as well. Those are examples of different scores. And so we'll do those before we calculate the other scores, or the other statistics that we'll use in our t-test. So to give a more concrete example here, let's say that we have this research question. If so we have a bunch of elementary school students. We're trying to get them to read, right? Because these kids these days, they don't want to read. They just want to be on their smartphones and whatnot. And so let's say we want to see if having a teacher around, having that supervision, if that will actually encourage elementary school students to read more. And so what we do is we have 2 reading sessions at 6 minutes each, and we record the time in seconds that each child reads during those 6 minutes, right? Or at least gives the impression of reading, right? Stares at their book intently, and at least is convincing the recorder that they're actually reading and not just daydreaming. And so in one session we have a teacher present, and the other the teacher's absent, right? They're not there. And importantly, now here we're looking at the same kids in each session, right? So we want to see if within the same people there's a difference. And so we record the difference, and so we have that on the table here. So in other words, each row represents a participant, a person. And then here we have 2 columns under teacher. One when the teacher's present, that's how many seconds they spent reading. and then when the teacher is absent, how many seconds they spent reading. Then we have different scores, right? So in participant 1, you can see that their different score was 10 seconds, right? So we can calculate those for our entire sample. And we want to test if there's a difference here at a 0.05 level of significance. Okay, so to do this, we follow our steps, starting with the first. And now our null hypothesis is a little bit friendlier again. So here we're just saying that there is no mean difference in time spent reading and the presence versus absence of a teacher, right? Mu sub d. And then with our alternative hypothesis, we're simply stating that there is a mean difference, right? Pretty straightforward. Set our criteria. Yeah, at this point, you understand this. Or I sure hope you do. If not, I failed you. So we found our critical t-value. We've got our rejection regions. We're doing a two-tailed test. We compute our test statistic. Here's our equation. Now we're going to compute the mean, variance, and standard deviation for different scores, right? In other words, we're going to calculate these values for our equation. And so m sub d. So now we're going to look at that table from the previous slide. Right, so here are different scores. Right, we're going to be using these values to inform this here. Right, and so yeah, we'll sum all those up and we'll get a score of 120. We had a total of 8 participants, right, or 8 different scores that we were assessing. We'll get a mean of 15. In other words, this is the mean difference score. So again, if we look at this, right, that's the mean difference score, the mean of the actual differences. And then if we look at variance, we'll calculate that accordingly. Yeah, using this formula here. And so again, if we're looking at the sum of squares, now we're squaring the different scores and then taking that sum to inform our sum of squares. So that's what's down here, sum of d squared, sum of the differences squared. So we'll plug those in. So we'll plug in, what was that, 3,400 here, and what was that, 120. Sorry, I'm bouncing around so fast. We'll plug in 120 here and 8 right there. And then we'll get, yeah, this value here, 228.57 for our variance. Right, sum of squares of 1,600. Hopefully this is making sense. If not, yeah, again, look at this table, compare it to the previous one. Compare it to how we calculated sums of squares in previous modules, and then hopefully that will help it click. Standard deviation, straightforward. Again, all these notations start to look different and more complex, but ultimately it's the same thing at its core. It's just a different way of expressing what we're trying to do. And so yeah, we'll calculate all these, and then we'll simply, we've got these. Now we need to calculate our denominator, the estimated standard error for different scores. So we just plug in our values for standard deviation and our sample size, or our sample of different scores, and then we'll get this, and then we plug it all in, we get our obtained t, we make a decision, we compare the two, what's our decision? Oh, 2.804, that's bigger than this, that's going to be in our rejection region. Huzzah, we're going to reject the null hypothesis, everything is right in the world, and we can say that elementary school children spent significantly more time reading in the presence of a teacher than when the teacher was absent. Statistics, right? That's what we can say. So I'll move quick through this one. So one more example of that was what, repeated measures on this. Now let's do matched pairs. So let's say psychologists tested whether older or younger twins are more or less introverted. So we have 7 pairs of identical twins, and we have their scores where higher scores indicate greater introversion. And then we have these different scores, and we want to test the null hypothesis that the mean difference in introversion scores between older and younger twins is 0 at an alpha of 0.05. Right? In other words, saying that there's no difference in introversion regardless of if twins are 6 years old versus 60 years old, right? So we have our steps here. Let's go through it. Our null hypothesis and our alternative hypothesis, same as what we just did on the previous one. Setting our criteria, right? Straightforward, nothing new or surprising here. We get our t crit, 2.441 or 2.447 plus or minus. We need to plug in our stats. We need to do the same thing we just did. Compute the mean, variance, and standard deviation. We plug in everything there. We're going back to our table and using that to calculate sum of d and the sum of squares. And then through that, we'll get our standard deviation, which we can use to plug in and calculate our estimated standard error. Then once we have that, we have these numbers. We can plug them in here, get our t obtained. That's a tiny t, 0.282. That is much smaller than our critical value. And therefore that will definitely not fall in the rejection region. And I'm tired. We decide to retain the null hypothesis. So if we want to write that up, we could say there were no significant differences in interperson scores between older and younger identical twins. T of 6 equal 0.282, P greater than 0.05. Right, and so if we want to calculate effect size here, again, nothing new. Here's a formula for you. Again, the same formula is for eta squared and omega squared, although d is slightly different. So if we wanted to calculate omega squared for this example, we can just plug in these values, right? And in fact, which one was that? Okay, I apologize. It's probably kind of jarring. This is not from 10.2. This is actually example 10.1, right? The previous one about elementary school children and reading, right? From this slide, right? This was our t-value there. So that's where that is coming from, right? So we plug that in, we can see that 46% of the variability in time spent reading could be explained by whether or not the teacher was present, right? So it seems like that actually does make a difference in this example. Anyway, hopefully the speed round wasn't too much for you. That is all I've got, so we'll see you around.